Hello everyone. So in this video, we'll talk about the first experiment of your DSP lab, the verification of sampling theorem. So what are we talking about here? What is this sampling theorem? So let us understand. So sampling theorem just says that if at all you want to have a analog signal, you want to convert it to digital, and once again, convert in discrete samples and reconstruct it back to the original form, then you have to make sure that number of samples, say, uh, I happen to have, right, say there is this particular wave which is analog. So the question comes in, you want to convert this to digital by taking discrete number of samples. How many number of samples you want to take per second? Are you happy with 100 samples per second, 1000 or 10,000? So it says that if at all you want to be able to, reconstruct the original signal from its samples, your sampling frequency has to be greater than or equal to twice the maximum signal frequency. That's the sampling theorem. And the equality here, 2FM, this is actually called as the Nyquist rate, okay, which forms the boundary. Okay, so for example, let us take this particular wave here. Okay, so I have taken this particular wave which is containing three frequencies. One is 100, and there is 150, and there is 175. Of course, a signal can have several frequencies. 175 here is the maximum signal frequency. So if at all I want to convert this particular analog signal to digital, and I want to be able to reconstruct the original signal from its samples, I better have my sampling frequency greater than 175 into 2. That's the sampling here. Okay. And what will happen if at all I'm taking more than that? Okay, suppose I'm taking 175 by into 2 is how much? What's the number? 350 maybe, right? So if at all I take 500 samples, better. 1000 samples, fine. Who's stopping it, right? But then what happens if at all you take less number of samples? So there will be two cases. The cases where you take number value, much greater than twice the maximum signal frequency. It's called as oversampling. Doesn't hurt, but then more number of samples means more number of memory, more number of processing time, more amount of bandwidth. Okay, so not a good idea though. And the other case is called as an undersampling. The other case is called as an undersampling, as I'm showing here. Okay, so the second case is called as undersampling, where your sampling frequency is less than the Nyquist rate, that is twice the maximum signal frequency. Now let us simulate the cases, and let us see, what's been done here, and what's the approach. So you will see two popular approaches in the verification of sampling theorem. I am using the frequency domain approach, where what I will do is I will take the fast Fourier transform. I will take a Fourier transform of the wave to show the individual frequencies, Okay, so let me go ahead. So what is the simulation environment here? I have taken samples, 1000 samples I have taken, and I keep a spacing of 1 by fs, right? That's the rule, right? Sampling frequency. How frequently have been taking samples? So I will take samples, 1000 samples I will take per second. That will be my sampling interval. Okay, that will be my sampling frequency. Okay, I should say. Okay, and what are the actual frequencies that I see? Remember, the frequency of the signal is different. Okay, which is the analog in nature. How frequently do I choose to take samples? That's what my sampling frequency. Okay, so here you can see A cos 2 pi ft, right? That's the usual thing we study, right? A cos 2 pi f, and instead of t I have an n here because my data is not analog anymore. It is discrete. It's not continuous, it is discrete. I take samples every 1 by fs. Okay, so here I have simulated this wave which contains three frequencies: 100, 150 and 175, and then I will plot the fast Fourier transform. Of course, when I take fast Fourier transform, I will use this ready function FFT. It's going to give me the magnitude and the phase angle. I am only interested in the magnitude. Okay, that's why I'm taking absolute of the fast Fourier transform. Let me run this thing. Let me run this first segment here and let me show you how the graph is going to be. You can see here, I use the command subplot 3, 1, 1. I want to have three graphs showing up here, one below the other, one for oversampling, one for Nyquist sampling, that is the boundary, and one for undersampling. Okay, so all three cases. So remember the frequencies that we chose. Okay, now let me take the cursor here. If it is, wait a second. Okay, so remember the frequencies that we had. The frequencies that we had in our case, they were 100. You can see an impulse at 100 as expected, an impulse at 150, and an impulse at 175. Okay, since we chose a sampling frequency as 1000, remember, as per the theorem, we could pick everything only up to 500. So all the values after 500, whichever you see on the right side of the graph, they are a simple replica or the mirror image or whatever that is there on the left side. Okay, so we are interested only from 0 to half the sampling frequency. So in the first case, my sampling frequency was 1000. So I am interested in only values from 0 to 500. And I look out for the frequencies that I gave. So I gave the frequencies 100, 150, and 175. And thank God, there is 100, there is 150, and then there is 175. Okay, so you can see here, this value is 150, and this one is 175, roughly there and there. Now let me go back. And take you to the other case. So in the second case, what I will do here, I will take the Nyquist rate, which is the boundary. Okay, Nyquist is the boundary. So maximum signal frequency is 175, 175 into 2, 350. This is the boundary. And now let me once again run the program. So here in the second case, I take a 350 point FFT. I take a 350 point FFT and I run the thing once again. So let us run this second segment in subplot 3, 1, 2. This is the second case. It's called as Nyquist rate sampling. Okay, not a suggested value. You are always supposed to have a value which is a bit higher than the Nyquist rate. So let me go to the figure and let us see if things are fine. Okay, are things fine? Here you can see there is an impulse at 100, fine. There is an impulse at 150, fine. And you can see at 175, you can see in the previous case at 175, you can see in this previous case, there was a, amplitude compared to the previous case. The amplitude was not that great. Okay, right. You can see here what has happened is an impulse on the left side and an impulse on the right side. Both of them have got added up. Because as I told you, you take more than twice the maximum signal frequency. Equality is called as the Nyquist rate. You should have taken 352, 354. That would be fine, but this is a boundary. Anyway, if at all we take till 350, from 0 to 350, our frequencies are there. Fine. Now let us go to the third case. The third case here, which is called as undersampling. Undersampling is a disaster where you can see something is happening. Unwanted guests are coming. Now let us see. I have taken a frequency of sampling frequency of 220. Now tell me, friends, if at all I take a sampling frequency of 220, which all frequencies do you see will be intact? So if at all the signal frequency should be, the sampling frequency should be twice the maximum signal frequency. So I think 175 into 2 is easily 350. So I think this is going to go. 150 into 2 is 300. That's also going to go. 100 into 2 is 150 into 2 is 300. Sorry, 100 into 2 is 200. Okay, probably this will be preserved. Okay, now let me take this thing and let me run this for you. Okay. So once again, before we go, let me tell you sampling frequency divided by 2. So when we took the first case, I told you if my sampling frequency is 1000, I am supposed to say everything from 0 to 500 or 499 to be precise. And here also 0 to 149 or 150 to be precise. Okay. So I have kept it very simple. I did not start my x-axis from 0. I started it from 1 to keep it simple. I do not want you guys to by heart. Okay, let's keep it simple. I thought, okay, let me run this thing now. Let me tell you once again, I have taken sampling frequency of 220. Okay, let's run this thing. Okay, so the output is here, and let us see what has happened. Okay, so surprise, surprise, surprise. As I told you, when I take a sampling frequency of 220, I am supposed to give values only till 220 divided by 2. Okay, and there is a grave problem. Of course, if at all you see the inspection directly, you have a value at 100, you have a value at 150. But who are these fellows? Who are these? Can you tell who are these? So this was not part of our plan. This was not part of one. There are two frequencies. There are two frequencies, one at 70, one at 45. Where did they come from? Where did they come from? Okay. So these are alien frequencies. Our original signal had values at 100, 150, and 175. Right here also 100, 150, and 175. Here, as I told you, in the entire fast Fourier transform graph, you only see till only half the values. That means I'm asking you to see only till 110, where you get the value 100. And then there are these two fellows here, one at 45 and one at 70. These are aliases. Okay, these are aliases. The whole problem is called as aliasing. Okay, this is what is going to happen when you do not want to spend on memory, you do not want to spend on bandwidth, you do not want to spend on the you know, uh, the power maybe, then you end up getting these fellows here. Okay, the problem is called as aliasing. That's why oversampling is good, but then it's going to cost you bandwidth, it's cost you speed, it's going to cost you memory. Nyquist rate is the boundary. Okay, undersampling is a disaster. Okay, so that's about sampling theorem.